There is no sunrise on this world. No pale edge of morning moves across the horizon. No star climbs into view, and no season turns the ice toward warmth. Above the surface, the sky remains almost perfectly black, interrupted only by distant points of light and the faint band of a galaxy through which the planet is traveling. It is a world without a sun. Astronomers call such objects free-floating planets, though they are often known by a more evocative name: rogue planets. Some may have formed around stars and later been expelled by gravitational encounters. Others may have formed in isolation from collapsing clouds of gas and dust, more like very small stars than displaced members of a planetary family. Their histories may differ, but their present condition is the same. They move through interstellar space without orbiting a parent star. They are not motionless, and they are not entirely unbound. Like stars, they continue around the center of the galaxy, following paths shaped by its gravity. What they lack is not direction, but a nearby sun. At the surface, a rocky rogue planet would be colder than any ordinary winter on Earth. Water would freeze. Most familiar atmospheric gases could eventually condense or settle onto the ground. Sunlight would contribute almost nothing, and the uppermost ice would become a rigid boundary between the planet and the surrounding dark. It would be easy to imagine that the story ends there. But a planet is not warmed only from above. Deep inside, heat can remain from its formation. Rock can release additional energy as radioactive elements decay. A large planet may cool slowly, holding part of its interior warmth for billions of years. If enough water covers the surface, and if the ice becomes thick enough, that frozen layer can act as insulation. The outer surface may remain locked at temperatures far below the freezing point of water, while far beneath it, pressure rises and heat escapes from the interior. Somewhere between the cold above and the warmth below, the temperature may reach the melting point. There, in some models, an ocean could begin. No such ocean has been observed on a rogue planet. No spacecraft has approached one, and even the planets themselves are difficult to find. Most produce little or no visible light. They reveal their presence only briefly, perhaps, when their gravity bends and magnifies the light of a distant background star, or when a young and still warm object glows faintly in infrared. So, the ocean beneath the ice remains a scientific possibility, not a discovery. Yet it is a possibility built from known physics. We have already learned within our own solar system that liquid water does not always need direct sunlight. Icy moons can hide oceans below frozen surfaces, sustained by internal energy and protected by layers of ice. A rogue planet would be a more isolated version of that idea, carrying its heat, its water, and perhaps its chemistry into the spaces between stars. Tonight, the journey moves inward. We will begin at the frozen exterior, then pass gradually through ice shaped by pressure, temperature, and time. We will follow the fading heat of a planetary interior and ask how long it might endure. We will look at the ways these worlds are formed, the ways they are cast away, and the faint signals by which astronomers try to count them. And beneath every layer lies one careful question: can a planet lose its sun, cross the galaxy alone, and still keep an ocean hidden inside? Before the ice became a roof, the planet belonged to motion. Most planets begin in a disk of gas and dust surrounding a young star. Within that disk, grains collide, cling together, and gradually build larger bodies. Over time, those bodies gather more material, disturb one another, and settle into orbits that may look orderly only after the system has survived its earliest confusion. A mature planetary system can appear permanent. The planets return along familiar paths. Their distances change in predictable ways. Their star remains at the center, and gravity seems to have arranged everything into a lasting design. But the beginning is rarely so settled. Young systems can contain more planets than they will eventually keep. Their orbits may be crowded, tilted, or slightly stretched, Small gravitational tugs accumulate each time one planet passes another. For thousands or millions of years, the changes may be almost impossible to notice. Then one close encounter alters the balance. A planet moving inward can steal a little orbital energy from another planet. A larger world can redirect a smaller one. Several encounters can follow, each changing speed and direction. The process is known as gravitational scattering, and it does not require a collision. The planets may never touch. Their gravity alone is enough to rewrite their paths. Sometimes one world is sent closer to the star. Another may be thrown onto a long, narrow orbit, and in some systems, one receives enough energy to escape entirely. Escape does not mean that gravity suddenly releases its hold. The planet must climb out of the star's gravitational well, losing speed as it travels outward. If it remains below the necessary escape speed, it will eventually turn and return. If it crosses that threshold, even by a small amount, the star can no longer call it back. The separation may unfold over years, centuries, or much longer. There is no sharp border painted across space. The star simply grows smaller, its warmth weakens. The old orbit opens into a path that will never close again. For a rocky planet, the consequences begin at the surface. Sunlight fades according to distance. At twice the former distance, the planet receives only 1/4 as much light. At 10 times the distance, only 1/100th remains. The air cools, clouds change, oceans begin to freeze from above. If the planet carries an atmosphere, parts of that atmosphere may eventually condense, depending on its composition and the pressure at the surface. Yet the deeper interior does not immediately know that the planet has been expelled. Heat, stored in rock and metal, continues to move outward. Radioactive elements continue to decay. A metallic core may continue to cool. If the planet has a moon, or more than one, some satellites might survive the ejection, though close gravitational encounters can also strip them away. The details depend on the violence of the departure and on how tightly each moon is bound. A planet can therefore lose its sky before it loses its inner activity. The ejection route is not the only possible origin for a free-floating world. Some planetary mass objects may form almost alone when a small cloud of gas collapses under its own gravity. In that case, the object is born in a way that resembles a star or a brown dwarf, but it never becomes massive enough to sustain ordinary hydrogen fusion. This creates a problem of language as much as astronomy. If two objects have the same mass, one may have formed in a disk around a star, while the other formed from a collapsing cloud. One would fit the usual story of a planet. The other would fit the usual story of a tiny substellar object. Seen from far away, after both have cooled, they might be difficult to distinguish. Mass alone does not always preserve history. For the world beneath our imagined ice, the ejection story matters because it offers a way to begin with water, rock, and a long-lived internal heat source. A planet formed near a young star could gather volatile materials, build an atmosphere, and perhaps spend part of its early life with liquid water exposed at the surface. Only later would the system become unstable. The timing could shape everything that follows. If the planet were expelled very early, while still hot from formation, its interior might contain a large reserve of energy. Its surface water could freeze gradually as starlight disappeared. A thickening shell of ice would reduce heat loss from the ocean below, slowing the planet's descent into cold. If ejection happened later, the interior would already have cooled. The planet might still preserve a buried ocean, but the duration would depend more strongly on its size, composition, radioactive inventory, and the thickness and behavior of the ice. There are also other paths into interstellar space. A passing star can disturb a planetary system, especially in a dense stellar nursery where young stars move relatively close to one another. A planet on a wide orbit is more weakly bound and easier to dislodge. Stars can create additional complexity. Much later, when a star loses mass as it ages, planetary orbits can expand and become less secure, allowing old instabilities to return. No single route is expected to explain every rogue planet. Some may be young giants, still glowing from formation. Some may be smaller worlds, expelled during the rearrangement of crowded systems. Some may carry moons. Some may carry atmospheres. Some may have lost nearly everything except rock, ice, and the heat sealed inside them. Their common feature is not a shared birth, but a shared condition. They have crossed from a local system into the galaxy at large. The change sounds dramatic when described from a human point of view, but the planet itself does not experience a moment of realization. Gravity has no ceremony. The last orbit does not announce itself as the last. The surface cools according to physical law. The interior releases heat at its own pace, and the surrounding stars slowly take on new positions as the world moves away from the place where it formed. Far behind it, the parent star becomes another point of light. Ahead, there is no destination. But beneath the freezing surface, the planet may still be carrying the conditions of its earlier life. Water remains water. Rock remains warm for a time. Pressure continues to rise with depth. The history of the lost star may survive not in the sky, but in the layers the planet takes with it. The first lasting structure on the wandering planet is not the ocean. It is the shell above it. As the world moves farther from its former star, the surface loses heat to space. Any open water cools from the top downward. Thin skins of ice, spread across lakes and seas, meet one another and thicken until the planet is covered by a continuous, frozen layer. At first, the change may still carry traces of the old climate. Snow may fall from clouds that formed while an atmosphere remained. Winds may move across the new ice. Storms could continue for a time, powered by heat escaping from the ocean and by differences in temperature from one region to another. But without sunlight, the atmosphere begins to lose its main source of energy. The planet continues radiating heat into space, and the gases above it cool with the ground. Water vapor freezes out early. Carbon dioxide may form frost or ice, depending on pressure. At lower temperatures, gases that remain airborne on Earth can also condense. An atmosphere rich in nitrogen or oxygen could gradually settle onto the surface as frozen deposits, leaving the air thinner than it was before. Not every rogue planet would follow this exact atmospheric path. A sufficiently massive world might retain a deep envelope of hydrogen and helium. Under high pressure, hydrogen molecules can absorb outgoing infrared radiation through interactions with one another, allowing a thick atmosphere to hold far more internal warmth than a thin, Earth-like atmosphere could. In some theoretical cases, that insulation might keep liquid water much closer to the surface, even without a star. But a smaller rocky planet may not keep such an envelope. It may have lost much of its light gas during formation, during ejection, or through later escape into space. For that kind of world, the atmosphere is unlikely to remain the main blanket forever. The enduring insulation would come from frozen water and the condensed remains of the air itself. Even after atmospheric collapse, the surface would not reach absolute zero. It would receive faint energy from distant stars, diffuse galactic light, and the cosmic microwave background, while heat continued to leak upward from the planet. Meteoroid impacts would add brief local pulses. These sources are small, but they prevent the exterior from becoming a place with no energy at all. The surface temperature would settle where incoming and outgoing energy balanced, while the deeper layers followed a much slower thermal history. The result would not necessarily be a bare sphere of water ice. The outermost layers might become a mixed archive of the planet's former sky. Frozen water could lie beneath deposits of carbon dioxide, nitrogen, methane, or other volatile materials. Dust delivered by impacts might gather between them. material released by cracks or brief eruptions could spread across older terrain. Each layer would record a different stage in the planet's cooling, though no observer would be present to watch the sequence unfold. The thickness of the ice would not increase at a constant rate. When the shell is thin, heat from below crosses it relatively easily. The base freezes, the surface radiates energy away, and the solid layer grows. As the shell thickens, however, the distance between the warm interior and the cold exterior becomes greater. Ice is not a perfect insulator, but a deep ice cover slows the transfer of heat. This is the same basic reason that a frozen lake can preserve liquid water below its surface through winter. The comparison is useful, though the scale is very different. On a rogue planet, the ice may extend not for inches or feet, but for many miles. The winter does not end, the darkness is not seasonal, and the heat below does not come from a coming spring, but from the planet itself. Near the surface, the ice would be hard and brittle. Temperatures there could remain so low that deformation happens only over immense spans of time. Impacts would fracture the crust. Stresses caused by cooling could open faults. If the planet retained internal activity, some cracks might reach downward into warmer layers, then close again as water or vapor froze inside them. Deeper down, the character of the ice would change. Pressure increases with depth because every layer carries the weight of everything above it. Temperature also rises toward the interior. Under those conditions, ice can bend and flow, even while remaining solid. Over long periods, the deeper shell may behave less like stone and more like a very thick, slowly moving material. Heat does not always pass through such a layer by simple conduction alone. If the lower ice becomes warm enough and mobile enough, it can begin to circulate. Warmer ice rises, cooler ice sinks. This process, called convection, can transport heat more effectively than conduction through a motionless shell. Whether convection develops depends on several properties at once: the shell's thickness, the temperature difference across it, the strength of the ice, and the amount of heat arriving from below. A shell that convects may settle into a different thickness from one that remains rigid. It may also create regions of compression and extension at the surface, though the details would depend on the planet's size and interior. The boundary between ice and ocean is not fixed in place forever. If heat from the interior weakens, part of the ocean freezes onto the base of the shell. If the heat flow rises, or if local geological activity concentrates energy beneath one region, some basal ice may melt. The lower surface of the shell could therefore change over time, gaining and losing material as the planet slowly cools. Salt and other dissolved substances would complicate this boundary. When water freezes, many salts are rejected from the growing ice crystals and remain in the liquid. The ocean below may become saltier as freezing continues. Salt usually lowers the temperature at which water freezes, helping some liquid persist under colder conditions. But the outcome depends on composition, pressure, and the chemistry of the original water. The ice itself may trap pockets of brine. Some could be small and temporary. Others might remain liquid in warmer regions near the bottom of the shell. These pockets would not prove that the planet supports life, but they would make the frozen layer less uniform than a simple drawing might suggest. At still greater depths, pressure can create forms of ice unlike the ordinary ice found at Earth's surface. Water molecules can arrange themselves into several solid structures. The familiar form in snowflakes, glaciers, and household ice is only one of them. Under high pressure, denser phases can appear. On a planet with a very deep global ocean, these high-pressure ices might form beneath the liquid water. That possibility matters because it can separate the ocean from the rocky seafloor. An ocean resting directly on rock can exchange minerals and chemical energy with the crust. If a thick layer of high-pressure ice lies between them, that contact becomes more limited. Heat can still move upward, and some material may be transported through the solid layer, but the chemistry would not be the same as it would be at an exposed rocky boundary. A world with too little water may freeze nearly solid. A world with enough water may preserve an ocean beneath ordinary ice. A world with far more water may build a layered interior, surface ice, liquid ocean, high-pressure ice, and then rock below. The phrase beneath the ice therefore hides a complex geography. There may be no single clean roof over a single open sea. There could be stacked layers with different crystal structures, bands of warmer and colder material, convecting regions, trapped brines, and a moving boundary where freezing and melting continue over geological time. The shell is not merely a lid. It controls how quickly the interior loses energy. It shapes the pressure inside the ocean. It influences whether the water touches rock. It may determine which chemicals remain available and which become sealed away. And it protects whatever lies below from interstellar space. Cosmic rays and other energetic particles strike the exposed surface. Small objects collide with the planet. The upper ice receives the full cold of the surrounding environment. But with depth, the influence of the outside galaxy weakens. Beneath enough material, conditions are governed less by passing radiation and more by pressure, chemistry, and the measured release of heat from within. Above the shell, the planet continues through a sky without daylight. Below it, temperature rises 1 degree at a time. The distance may be great, but the direction is simple. Downward through frozen atmosphere. Downward through brittle crust. Downward through ice that can flow across ages. And somewhere beneath that weight, the solid structure may finally give way to water. A hidden ocean can survive only if the planet continues to supply heat from below. That heat does not come from a single furnace. It is the combined result of several processes, each beginning at a different stage of the planet's history and fading at its own pace. The first source is the energy of formation. A rocky planet is assembled through collisions. Small bodies strike larger ones. Their motion is converted into heat. Material is compressed under growing weight, and the interior becomes hot enough for parts of it to melt. Dense metals sink toward the center, while lighter rock rises above them. This separation, known as differentiation, releases additional energy as the planet reorganizes itself into a core, mantle, and crust. Much of that early heat eventually escapes. The surface radiates it into space. Volcanoes carry hot material upward. Cracks, impacts, and the movement of rock provide pathways through which energy can leave. A small body loses heat more quickly because it has more surface area in relation to its volume. A larger planet keeps it longer, protected by the thickness of its own interior. This difference is important for a world traveling without a star. A small rogue planet may cool until most of its internal activity becomes weak. A more massive rocky world can remain warm inside for far longer. The same bulk that increases pressure also increases the amount of stored heat and lengthens the path that heat must cross before reaching the surface. Yet, stored heat alone may not be enough to preserve an ocean over billions of years. The planet also needs a source that continues after formation. That source can be found in the atoms inside its rocks. Certain elements are unstable. Their nuclei change over time, releasing energy in the process. Uranium, thorium, and potassium are among the most important heat-producing elements in rocky planets. They are present only in small amounts, but some decay so gradually that they can continue warming the mantle long after the surface has frozen. Radioactive decay is not a fire. It does not require oxygen, and it does not arrive in bursts. It is distributed through minerals atom by atom, producing a broad background of heat across geological time. On Earth, this process contributes to the energy that drives mantle motion through volcanism and the long cooling of the interior. A rogue planet with a similar rocky composition could carry the same kind of heat source into interstellar space. Losing sunlight would not stop the decay. The atoms would continue changing at the same measured rates, whether the planet orbited a star or crossed the dark between them. The amount of radiogenic heat would depend on where and how the planet formed. Young stars and their surrounding disks do not all contain identical mixtures of elements. A planet born from material rich in uranium, thorium, and potassium could remain geologically active longer than a similar world formed with less. Its size would matter. Its mantle chemistry would matter. The way heat-producing elements were distributed during differentiation would matter. This makes the lifetime of a buried ocean a question of planetary biography. Two worlds with the same surface temperature and the same amount of water might have different interiors. One could maintain mantle convection and local melting. The other might have cooled into a state where heat moves outward only weakly. From a distance, both would appear almost equally dark. Beneath the ice, their histories would have led to different oceans. Heat leaving the interior does not rise through rock, a straight, uniform stream. In the mantle, warm material can become buoyant and rise, while cooler material sinks. This circulation moves heat across great distances over long intervals. The rock remains solid for much of the process, but under sustained pressure and temperature, it can deform and flow. Where rising mantle begins to melt, magma may form. If that magma reaches the base of an ocean, it can build volcanic structures on the seafloor. If seawater enters cracks in warm rock, it may circulate downward, absorb minerals and heat, and rise again through hydrothermal systems. No hydrothermal vent has been detected on a rogue planet. The idea follows from processes observed on Earth and considered for ocean worlds in our own solar system. It is one possible consequence of placing liquid water above a geologically active rocky interior. Such systems would matter for more than temperature. Water reacting with rock can change the chemistry of both. Minerals dissolve, new compounds form. Chemical gradients appear between fluids that have passed through hot crust and the colder water around them. On Earth, these gradients support ecosystems that do not depend directly on sunlight. That comparison must be handled carefully. The existence of hydrothermal energy does not guarantee life. Liquid water does not guarantee life. A stable ocean, useful chemistry, and a continuing energy source would provide conditions that biology might use, but they would not show that biology had begun. A buried rogue planet ocean could remain entirely lifeless. Even so, the possibility changes what darkness means. A world without daylight need not be a world without active chemistry. Its most important environment could lie beyond the reach of starlight, powered by the cooling and alteration of its own interior. There may be another source of heat if the planet carries a moon. A satellite raises tides in its planet, and the planet raises tides in the satellite. If the orbit is not perfectly circular, or if the moon's rotation and orbit interact in the right way, repeated flexing can convert orbital energy into heat. Within our solar system, tidal heating strongly affects several moons. It can maintain internal activity where sunlight alone would be insufficient. A rogue planet that retained one or more moons after ejection might preserve a similar source, but survival through ejection would not be assured. A distant moon is weakly bound and could be stripped away during the same encounter that removes the planet from its star. A close moon has a better chance of remaining attached, though the gravitational disturbance could alter its orbit. In some cases, the new orbit might increase tidal heating. In others, later interactions could reduce it or cause the moon to collide, escape, or spiral inward. Tidal energy is also not permanent in the same way that radioactive decay can be long-lived. It changes the orbit that supplies it. Over time, tides can circularize an orbit, alter rotation, and reduce the very flexing that produced the heat. For this reason, a moon could extend the warmth of an ocean without serving as an endless power source. The most durable picture is likely to involve several forms of energy working together. Primordial heat supplies a large early reserve. Radioactive decay adds energy over long periods. Mantle motion carries that heat toward the outer layers. Local volcanism or hydrothermal circulation may concentrate it at the sea floor. Tides, if a moon remains, may contribute another layer of heating. Above all of this, the ice controls how quickly the energy is lost. A planet does not need to generate enough heat to warm its surface. It needs only to provide enough upward flow that, beneath sufficient insulation, part of its water stays above the local melting temperature. That requirement is smaller than it first appears. The outer shell can be extremely cold while the base remains near melting. The temperature difference is spread across many miles of ice. Heat crosses that distance slowly. If the shell thickens as the planet cools, it can reduce further losses, creating a kind of thermal adjustment between the interior and the ocean. There are limits to this protection. If heat production falls too far, the ocean freezes from the top and perhaps from the bottom as well. If high-pressure ice separates the water from rock, chemical exchange may weaken. If the mantle becomes rigid, volcanism can diminish. A magnetic field may fade as motion in a metallic core slows, though the presence or absence of such a field would not determine whether liquid water survives beneath a deep shell. The planet's fate would therefore fold gradually. There would be no single night when the ocean vanished. Ice would accumulate at its boundaries. Salts would become concentrated in the remaining liquid. Circulation would change. Regions above warm crust might persist after colder basins had frozen. Small reservoirs could remain in places where heat was focused. The last water might not form one global sea. It could survive as connected layers, deep pockets, or narrow zones above active rock. The interior would become a map of uneven warmth, shaped by composition and geological history rather than by latitude or season. On Earth, the warmth beneath your feet is easy to overlook because sunlight dominates the surface. Day arrives, weather moves, and the upper world receives a constant supply of energy from the sun. Yet far below, the planet carries another history, one that began during formation and continues through the decay of atoms and the motion of rock. A rogue planet would depend almost entirely on that inner history. Its surface would offer no sign of an ocean. No reflected blue light would reveal it. No cloud pattern would move above it. The evidence, if astronomers ever found a way to gather it, would have to come indirectly from mass, composition, thermal emission, or some future measurement capable of probing beneath a frozen exterior. Until then, the ocean remains hidden not only by distance but by the nature of its heat. It is warmed by processes too gradual to shine. And while the planet travels between stars, the energy stored during its birth continues its long passage outward, from core to mantle, from mantle to water, and from water into ice. Liquid water beneath the ice would not resemble an open ocean under a familiar sky. There would be no wind at the surface, no waves shaped by weather, and no sunlight passing through clear water from above. The ocean would begin beneath a ceiling of ice and extend downward into a region defined by pressure, heat, dissolved minerals, and the slow movement of water through darkness. Its circulation would be driven from within. Heat rising from the rocky interior could warm the deepest water. Warmer water may become buoyant and move upward, while cooler water near the ice descends. Salinity would influence the pattern, so would pressure, the shape of the sea floor, and the way the ocean exchanges heat with the frozen shell above it. The motion might be broad and continuous, or divided into separate regions that mix only gradually. Without continents exposed above the water, there would be no coastlines in the usual sense. Yet underwater ridges, basins, volcanic rises, and fractures could still guide currents across the hidden seafloor. If the ocean were parcel of water might spend centuries moving between warmer depths and colder upper layers. If the circulation were weak, some regions could remain chemically isolated for much longer. The ocean's composition would begin with the materials gathered during the planet's formation. Water ice arriving in small bodies could carry carbon-bearing compounds, salts, ammonia, sulfur, and other substances. Rock beneath the ocean would contribute additional elements. The atmosphere that existed before ejection might dissolve gases into the water, leaving a chemical memory of the planet's earlier environment, even after the surface had frozen. As the ice shell grew, freezing would change that chemistry. Pure water molecules tend to join the crystal structure of ice more easily than many dissolved salts do. Much of the salt would remain behind in the liquid. Over time, the shrinking ocean could become more concentrated, though some material would also become trapped in the ice or deposited as minerals. The exact result would depend on how quickly freezing occurred and how the ocean circulated. A rapidly advancing ice boundary might trap pockets of salty water. A slower process could separate liquid and solid more efficiently. Chemical compounds might settle onto the seafloor, remain dissolved, or become incorporated into unfamiliar forms of ice under pressure. Ammonia, if present, could lower the freezing point of water. Salts can do the same. These substances would not create heat, but they could allow liquid to remain at temperatures where purer water would freeze. A buried ocean may therefore survive through a combination of insulation, internal energy, pressure, and chemistry. None of these conditions would make it Earth-like. The water could be far saltier than Earth's oceans. It might contain large amounts of dissolved carbon dioxide or ammonia. Its acidity could differ greatly from place to place. The pressure at the bottom could exceed that of Earth's deepest trenches many times over, especially on a large planet with a deep water layer. Yet these differences would not make the ocean inactive. Where water meets warm rock, chemical reactions can release energy. One of the most discussed processes involves water entering cracks in rock that contains minerals rich in iron and magnesium. The water reacts with those minerals, changing the rock and producing new compounds. Under suitable conditions, the process can generate hydrogen. This broad family of reactions includes serpentinization. On Earth, serpentinization occurs in parts of the seafloor where seawater circulates through certain kinds of mantle-derived rock. It can create hydrogen-rich fluids and support chemical environments that microorganisms may use. The process does not require sunlight. It requires water, reactive rock, and temperatures that allow the reactions to proceed. A rogue planet with a rocky sea floor could, in principle, provide those ingredients. Water might descend through fractures created by cooling, tectonic stress, or volcanic activity. As it moved through warmer rock, it could dissolve minerals and take part in reactions. The altered fluid could then rise, carrying heat and chemical compounds back into the ocean. At the seafloor, it might emerge through vents. Some vents could release very hot fluids. Others might be cooler and more alkaline. Minerals carried by the water could precipitate when the fluid mixed with the surrounding ocean, gradually building towers, crusts, or porous structures. These structures would be important because they create boundaries. Inside a mineral wall, one chemical condition can exist. Outside it, another can remain. Differences in acidity, temperature, and composition can produce gradients, and gradients can store usable energy. Life on Earth depends on gradients at every scale. Cells maintain differences between their interiors and the surrounding environment. Organisms use chemical imbalances to move electrons, build molecules, and preserve order. Sunlight creates many of the largest energy gradients at Earth's surface, but it is not the only source. In the deep ocean, entire ecosystems can be supported by chemosynthesis. Microorganisms use chemical reactions rather than light to build organic matter. Some rely on hydrogen sulfide. Others use hydrogen, methane, iron, or additional compounds. Larger organisms may then depend on those microorganisms directly, or through symbiotic relationships. This is one reason hydrothermal systems attract such interest in the study of life beyond Earth. They show that an environment can remain biologically productive without receiving sunlight. They also bring together liquid water, rock, energy, and complex chemistry in one place. But an analogy is not evidence. Earth's deep sea life did not necessarily begin at the vents where it now survives. Its history is connected to a planet with a sunlit surface, a long-lived atmosphere, active plate tectonics, and billions of years of changing environments. A rogue planet would begin from a different set of conditions. Even if it carried life before ejection, the transition into interstellar space could be severe. Surface ecosystems would lose light. Photosynthesis would stop, except perhaps for organisms using stored or artificial sources that nature would not provide. Temperatures would fall. The atmosphere could collapse. Habitats connected to sunlight would disappear as the ice advanced. Life already established beneath the surface might have a better chance. Microorganisms living in rock, sediment, or hydrothermal systems would be sheltered from the rapid changes above. Their energy supply could continue as long as water circulated and chemical reactions remained available. The growing shell might even protect the ocean more effectively as the planet cooled. If the ejection happened early, before life arose, the question would be harder. Could life begin in an ocean that had never known sunlight? There is no confirmed answer. Some hypotheses for the origin of life place important steps near hydrothermal environments where mineral surfaces, heat, and chemical gradients could help organize simple molecules. Other models emphasize shallow pools, wet and dry cycles, ultraviolet light, or surface chemistry. Earth preserves no complete record of the first transition from chemistry to biology, so scientists cannot yet say which environment was necessary. A rogue planet may lack many conditions available on early Earth. It may have no repeated drying and refilling of surface pools. It may receive very little useful ultraviolet radiation beneath the ice. Organic molecules in the ocean could become too diluted unless currents, pores, mineral surfaces, or freezing processes concentrated them. Yet the hidden world could offer other forms of concentration. Porous vent structures might hold molecules close together. Mineral surfaces could encourage reactions. Ice forming above the ocean could exclude salts and organic compounds, collecting them in briny channels. Impacts before the shell became thick might deliver carbon-rich material. The planet's original atmosphere and oceans could already contain a complex mixture assembled during formation. The question is not whether life would certainly appear. It is whether the planet could preserve enough energy and chemical variety for the possibility to remain open. That possibility would depend strongly on time. A hydrothermal system lasting a few thousand years might create interesting chemistry without allowing long biological development. A stable ocean maintained for hundreds of millions or billions of years would offer a far longer interval for reactions, selection, and adaptation. The planet's cooling rate would set part of that clock. So would the supply of reactive rock. Chemical energy can be consumed if water alters the accessible minerals and no geological process exposes fresh material. The useful gradients may weaken. Volcanism, faulting, mantle circulation, and crustal renewal could extend the supply by bringing new rock into contact with the ocean. On Earth, plate tectonics continually reshapes the surface and recycles material between the crust and mantle. A rogue planet would not necessarily have plate tectonics. Its outer rock might form one rigid shell, broken only locally by stress and volcanism. Even limited activity could matter. A fracture opening across the seafloor could expose fresh minerals. A volcanic eruption could add heat and new material. The cooling of magma could drive water circulation for thousands of years. Separate regions might become active at different times, creating a scattered network of chemical environments rather than one permanent center. If organisms existed there, they might remain microscopic. There is no reason to assume a hidden ocean would produce large animals, complex ecosystems, or anything recognizable from Earth's surface. Limited energy often favors small, slow-growing life. Populations might cluster near vents, within sediments, or inside the rock itself. Their world would be measured in chemical boundaries rather than seasons. They would not respond to sunrise. They might never experience radiation from a nearby star. The motion of the planet through the galaxy would have almost no direct meaning at the seafloor. Above them, constellations would shift over millions of years as the planet crossed interstellar space. Nearby stars would pass and recede. The frozen surface might occasionally receive a little more light during a distant stellar encounter, though not enough to transform the deep ocean below. At the bottom, the more important events would be local. A crack opening, warm fluid entering cold water, minerals forming along the edge of a vent, a chemical imbalance lasting long enough to be used. The energy available in such an environment would be modest compared with the sunlight reaching a habitable planet's surface. But biology, where it exists, does not require abundance in every place. It requires pathways by which energy can be captured, and enough stability for those pathways to continue. A rogue ocean might provide narrow pathways for a very long time, and if life had begun before the planet was expelled, those pathways could become refuges. Imagine the final daylight fading from the upper ocean as ice closes above it. Organisms near the surface disappear or descend. The environments already accustomed to darkness continue. Generation after generation, the living world contracts toward the heat below. The old star becomes invisible, but its earlier influence remains in the water, in the carbon, in the salts, and perhaps in the descendants of life that began while the planet still had a sky. Far beneath the frozen surface, survival would not depend on remembering the light. It would depend on what the rock and water could still provide. The planet may carry an ocean for billions of years and still remain almost impossible to recognize from Earth. A world like this produces no reflected daylight of its own. If it is old and rocky, most of the heat left from formation has faded into a weak infrared glow. Against the background of the galaxy, it would be smaller than a point, colder than the objects that ordinary planet searches are built to find, and separated from us by distances that turn even large worlds into nearly nothing. Astronomers, therefore, do not usually discover rogue planets by seeing their surfaces. They find the effects those planets have on light. The most important method is gravitational microlensing. It begins with a distant background star and a second object passing almost directly between that star and Earth. The intervening object may be another star, a brown dwarf, a planet, or something else with enough mass to bend the path of light around it. The foreground object acts like a lens made by gravity. It does not produce a sharp image like a glass lens. When the alignment is close enough, the background star briefly appears, brighter, as its light is redirected around the foreground mass. The rogue planet may remain completely dark. For a time, the star behind it changes. A microlensing event caused by a star can unfold over weeks or months. Lower mass lenses generally produce shorter events. A free-floating planet may create a brightening that lasts for only days, or in some cases hours, depending not only on its mass, but also on the distances and relative motions involved. The event has to be caught while it is happening. Astronomers monitor crowded fields containing millions of stars, often toward the central regions of the Milky Way. Computer systems compare one image with the next, looking for points of light that rise and fall in the smooth symmetrical pattern expected from lensing. Most of those stars remain unchanged. Some vary because they pulse, flare, or eclipse one another. A few brighten because an unseen object has crossed the narrow line of sight needed for microlensing. The alignment is accidental. It may never repeat. Once the lens has passed, the background star returns to its previous brightness. The planet continues along its path, and the opportunity to study that particular event is largely gone. This makes microlensing both powerful and incomplete. It can reveal objects that emit almost no light, including planets far from stars and planets with no detectable host. It does not require a repeating orbit, but the first observation often gives astronomers only a timescale and a light curve. A short event suggests a low-mass lens, yet duration alone does not provide a unique mass. A nearby light lens moving slowly can resemble a heavier lens farther away, moving more quickly. Several arrangements can leave nearly the same brightening pattern. Additional effects can break part of this uncertainty. If the finite size of the background star changes the shape of the event, astronomers may estimate the angular scale of the lensing geometry. If the event is observed from widely separated locations, such as Earth and a spacecraft, the two viewpoints can reveal a microlensing parallax. Very precise measurements of how the apparent position of the source shifts may add further information. When these pieces are combined, the lens mass and distance can sometimes be constrained far more closely. Yet even then, an important question remains. Is the object truly alone? A planet on a very wide orbit around a faint or distant star can produce a short lensing signal that looks similar to one from a free floating planet. If the host star is far enough from the planet in projection, its gravitational signature may not appear clearly in the brief event. Astronomers search for a second, broader feature in the light curve. They inspect deep images for light from a possible host. They return later, after the source and lens have moved apart on the sky, hoping that improved resolution will reveal a star near the path of the event. Sometimes no host is found. That absence places limits on what could be hiding there, but it may not prove complete isolation. The possible star could be too faint, too distant, or too widely separated to detect. For this reason, many low-mass rogue worlds first enter astronomy as candidates. Their signals can be convincing without providing every detail of their identity. A candidate may be consistent with an Earth mass or Mars mass free-floating planet, while still allowing a range of lens masses or a remote host that has not been ruled out. The uncertainty is not a flaw in the work. It is part of what the light contains. A microlensing event is a brief geometric encounter involving an unseen lens, a distant star, and a moving observer. Astronomers recover what they can, then describe the possibilities the measurements permit. The other major route to rogue planets begins with heat. Young planetary mass objects can remain warm after formation. Their interiors release stored energy, and their atmospheres emit infrared radiation. Unlike an old rocky world, a young object with several times Jupiter's mass may be bright enough in infrared light to image directly with a large telescope. These discoveries often occur in young star-forming regions or nearby moving groups. A faint infrared source traveling with the group may be a very low mass brown dwarf or a planetary mass object formed in isolation. Spectroscopy can reveal water vapor, methane, carbon monoxide, clouds, and other atmospheric features. The object's brightness and temperature can be compared with cooling models to estimate its mass. But those estimates depend on age and formation history. A young object cools and dims with time. Different masses can show similar temperatures at different ages. Models must also describe clouds, early cooling, and atmospheric gravity. There is no perfectly clean boundary between the lightest brown dwarfs and the heaviest free-floating planets. Some researchers use formation as the distinction. A planet forms in a disk. A brown dwarf forms through direct collapse. But formation history is difficult to reconstruct for an isolated object. Others use mass-based categories connected with whether deuterium fusion can occur. That threshold is useful in some contexts. But nature does not divide every object at one exact number. Composition affects the threshold. And mass alone does not reveal whether the body was born beside a star or alone in a cloud. The words remain practical labels, placed over a continuous range of objects. For the question beneath the ice, this difference matters. Direct imaging currently favors young, warm, relatively massive bodies. These may be gas-rich objects without a solid surface or global water ocean. Microlensing can reach much lower masses, including worlds that may be rocky, but it usually tells us little about their temperature, atmosphere, water inventory, or interior. The worlds easiest to study are not always the worlds most likely to match the hidden ocean we are imagining. An old Earth-sized rogue planet could pass through the field of a survey, magnify a background star for a short interval, and then disappear into the dark with almost all of its physical character unknown. Astronomers might estimate its mass. They might constrain its distance. They might find no nearby host. They would still not know whether the planet carried one layer of ice or 100 miles of it. They would not know whether radioactive elements warmed its mantle, whether salt lowered the freezing point of an ocean, or whether a moon remained in orbit. Detection is only the first boundary. The next generation of wide-field surveys is designed to watch dense regions of the sky, with the cadence and precision needed to capture many more microlensing events. NASA's Nancy Grace Roman Space Telescope, observing above Earth's atmosphere, is expected to make a large census of planets found through lensing, including free-floating candidates at masses lower than ground-based surveys can routinely reach. The purpose of such a census is not merely to collect unusual worlds. Their abundance would test how planetary systems form. If low-mass rogue planets are very common, young systems may eject small worlds efficiently. If more massive isolated objects dominate, direct collapse may contribute a larger share. The distribution of masses can preserve evidence of crowded beginnings that no telescope can watch directly. Counting them is difficult because every detection method favors a different part of the population. Infrared surveys favor warm and massive objects. Microlensing favors chance alignments and brief changes in distant starlight. Nearby, old rocky rogues may be too cold for direct imaging and may never pass in front of a suitable background star during the years we are watching. Any estimate of their total number must account for the worlds the survey was unlikely to see. That is why predictions have ranged widely. Astronomers have proposed populations from relatively modest numbers to many free-floating worlds for every star, depending on the masses considered, the candidate samples used, and assumptions about detection efficiency. A stronger survey does not merely add more objects. It narrows the uncertainty around the invisible population. While you rest beneath an ordinary night sky, the light used for this search is already moving through the galaxy. It leaves a distant star, bends for a moment around a planet no one can see, and continues toward a detector near Earth. Nothing on the rogue world needs to glow. Its gravity is enough. For a few hours, perhaps a few days, the hidden planet writes a small curve into the brightness of another sun. That curve may be the only message it ever gives us. From it, astronomers begin with mass and motion. The ice, the ocean, and the heat below remain beyond the measurement, waiting behind a darkness that gravity can reveal, but not yet open. The space between stars is not empty, and the wandering planet does not cross it without influence. Thin gas extends through the galaxy, Dust grains move between stellar systems. Magnetic fields thread broad regions that cannot be seen with ordinary eyes. High-energy particles arrive from distant events, passing through the exposed surface and sometimes penetrating deep into the frozen ground. Yet for most of the planet's journey, these surroundings would be too diffuse to change its course or warm its ocean. A world has too much momentum to be slowed by the sparse gas between stars. Individual atoms strike its atmosphere or surface, but their combined effect across ordinary spans of time remains small. Dust leaves tiny impact marks. Larger objects occasionally release flashes of heat. None of these provides a new climate. The planet continues along an orbit around the center of the Milky Way. Its path may differ slightly from that of nearby stars because of the speed and direction it received during ejection. It may move above and below the galaxy's disk. It may pass through spiral regions where stars and gas are more concentrated, then return to areas where the distances between systems are greater. One circuit of the galaxy would require hundreds of millions of years. During that interval, the constellations above the planet would not remain fixed. Nearby stars would shift across the sky as each followed its own galactic path. Familiar patterns from the planet's original system would stretch apart and disappear. New arrangements would form, remain for a time, and slowly dissolve. There would be no observer on the frozen surface to name them. Beneath the ice, these changes would have almost no immediate effect. The ocean would respond to the cooling interior, the movement of its water, and the chemistry of the seafloor. The changing sky would remain separated from it by miles of frozen material. The planet's most important external encounters would involve other stars. Stars are widely spaced in much of the Milky Way. A rogue planet can travel for an immense interval without passing close enough to one for the encounter to matter. Even when a star appears bright in the sky, it may remain thousands of times farther away than Earth is from the Sun. At those distances, the added warmth would be negligible. A closer passage is possible, especially during the planet's early life if it was expelled inside a crowded stellar nursery. Young stars often form in groups, and the spaces between them can be smaller than those in the region where the Sun now resides. A newly ejected world may pass other stars before leaving the cluster in which it was born. Each encounter changes its path by some amount. A distant star produces only a small deflection. A closer one can noticeably alter the planet's direction and speed. The same encounter might disturb a moon, stretch its orbit, or remove it from the planet altogether. If the rogue world carries a satellite that supplies tidal heating, this is more than an orbital detail. Losing the moon could reduce one of the ocean's energy sources. A change in the moon's orbit could temporarily increase tidal flexing, producing more heat before the orbit gradually evolves again. The fate of the hidden ocean may therefore be influenced by events far above it, even when no starlight reaches the water directly. A sufficiently close stellar passage would also brighten the surface. At first, the star would appear as one point among many. Across centuries or millennia, depending on its speed and distance, it might grow brighter. Shadows could return to the ice. Frozen gases near the surface might warm or begin to sublime. A thin temporary atmosphere could form from material that had rested on the ground since the planet's first cooling. But the effect would depend on how close the planet came. Most encounters would provide with too little energy to create liquid water at the surface. A star would need to pass at planetary system distances before its radiation became comparable to the sunlight received by ordinary planets. Such encounters are far less common. Even then, the warming might not last long enough to thaw a deep ice shell. Heat moves through thick ice slowly. The surface could respond, while the ocean remained buffered below. Much as a brief change in weather does not immediately reach the bottom of a glacier. The upper layers might fracture as temperatures changed, Volatile deposits could migrate from colder regions to warmer ones. Frost could rise into a temporary sky and fall again after the star receded. For the buried ocean, the passing sun might be little more than a distant event recorded near the top of the shell. A much closer approach would carry risks. The star's gravity could accelerate the planet, disturb its moon, or pull it onto a new trajectory. If the passage brought the planet too near, tides could deform its interior. The encounter might add heat, but it could also fracture the crust, reshape the orbit of any satellite, or strip loosely held gases and debris. There is a narrow range between an encounter that does almost nothing and one that changes too much. The most striking possibility is capture. A rogue planet could, under the right conditions, become part of another stellar system. Yet capture is not as simple as passing near a star and being pulled into orbit. In an encounter involving only one star and one planet, the planet falls inward, gains speed, swings around the star, and leaves again. The energy gained during approach is returned during departure. Unless something removes part of that energy, the path remains open. Permanent capture requires another participant or a changing gravitational environment. A binary star can exchange energy with the incoming planet. A star that already has planets can do the same through a multi-body encounter. In a young cluster that is expanding and dispersing, the broader gravitational field can change while objects move through it, allowing some free-floating planets to become loosely bound to stars. These captures are possible, but their results may look unlike the orderly planetary systems imagined around a single sun. A captured world could settle into a very wide orbit. Its path might be strongly elongated, carrying it relatively close to the star for part of the orbit and far into the cold for the rest. Its orbital plane may be tilted compared with planets that formed in the star's disk. It could even orbit in the opposite direction. The new sun would not erase the planet's history. The ice would still contain layers formed during interstellar travel. The ocean would still depend on stored heat and radioactivity, unless the captured orbit brought the world close enough for starlight to become important. Its chemistry would still reflect the materials gathered around another star, perhaps in a different region of the galaxy. It would be an adopted planet carrying the interior of an older system. If its orbit remained wide, the surface might continue to be frozen. The star could become the brightest object in the sky without providing enough warmth to reach the ocean. A complete orbit might take thousands or millions of years, producing a cycle too long to resemble any familiar season. On an eccentric path, the planet could receive brief periods of stronger heating near the star, followed by long returns to the outer system. Frozen atmospheric gases might rise and fall with each passage. Surface ice could expand, contract, and crack. If the heating became strong enough, temporary lakes or thin melt layers might form into places where the shell was dark, fractured, or warmed from below. The deeper ocean would respond more gradually. A planet captured into a closer and more stable orbit could enter an entirely new phase. Over time, the surface might warm enough to release an atmosphere. Ice could melt from above as well as below. Gases buried for ages might return to the sky. But a new orbit would not guarantee a habitable surface. The star could be too bright, too active, or too faint. The planet's atmosphere might not rebuild in a useful form. Its water could lie beneath a high-pressure structure that did not melt easily. A close encounter capable of capture might also leave the orbit unstable. Capture is not a rescue. It is another physical transition. The planet may never experience it. Most rogue worlds are likely to remain free for intervals longer than the lifetimes of many stars. They continue around the galaxy, passing through changing environments, without entering another system closely enough to stay. Their futures are then governed primarily from within. The radioactive elements in the mantle decline according to their half-lives. The core releases the heat it can still carry. The ocean freezes gradually as the flow from below weakens. Salts and other compounds become more concentrated in the remaining liquid. If geological activity continues unevenly, the global ocean may divide into smaller reservoirs. Warm regions could persist above mantle upwellings or long-lived volcanic provinces. Elsewhere, ice could extend all the way to the rocky crust. A moon, if one remains, may keep certain regions active through tidal flexing. Its orbit will also evolve, changing the amount and location of the heat it supplies. Eventually, the difference between an ocean world and a frozen world may become difficult to define. Thin films of water could remain along mineral boundaries. Brines might survive in deep pockets. Warm fractures could hold liquid after larger basins have solidified. The planet may lose its ocean as a connected place while preserving water in scattered environments far below the surface. The end would not arrive everywhere at once, and the end may not be permanent. A later tidal disturbance, an episode of volcanism, or capture by a star could melt part of the interior ice again. Water that had remained solid for millions of years might return to liquid in a limited region. The history of the planet would be written through alternating boundaries, rather than a simple path from warm to cold. Across that history, the galaxy continues around it. Stars are born in clouds the planet may pass at a distance. Other stars age and shed their outer layers. Supernovae release energy far away. Stellar groups form, disperse, and lose their original shapes. The rogue world belongs to none of them, but it remains inside the same galactic system. Its isolation is local, not absolute. Gravity still guides it around the Milky Way. Matter still reaches its surface. Passing objects still alter its motion. Somewhere in its interior, rock and water continue exchanging heat, long after the star of its birth has become indistinguishable from all the others. And if another sun ever finds it, that sun will meet a planet already carrying an entire climate beneath the ice. Finding a rogue planet would not be the same as finding its ocean. The first evidence might reveal only that an unseen mass had passed between Earth and a distant star. From the duration and shape of the brightening, astronomers could estimate a range of possible masses. With additional measurements, they might narrow the planet's distance and motion. None of this would show what covers the surface. To reach the hidden water, science would have to proceed through layers of inference. The first question would be size. Mass alone cannot tell us whether a planet is made mostly of rock, water, gas, or some combination of all three. A dense rocky world and a larger water-rich world could produce similar gravitational effects. Astronomers would need an independent measurement of radius, and obtaining one for a cold object that does not transit a nearby star would be difficult. If the planet passed in front of a distant background star, a precise occultation might reveal its width by measuring how long the star's light disappeared. But such alignments would be rare, and a small atmosphere could complicate the edge of the event. Direct imaging might provide another route for a nearby object that still emitted enough infrared radiation, though an old Earth-sized rogue would be faint beyond the reach of most present instruments. A radius combined with mass would provide average density. That would not offer a complete interior map, but it could separate broad possibilities. A high density might suggest a world dominated by rock and metal. A lower density could point toward a large fraction of water, ice, or retained gas. The next question would be heat. A planet with no sun can reveal its internal energy through thermal radiation. Every object above absolute zero emits some form of light. For a cold rogue planet, most of that emission would fall at infrared wavelengths longer than human eyes can detect. The amount and pattern of thermal radiation could constrain the surface temperature. If the temperature were higher than expected from the surrounding starlight alone, The difference might indicate heat escaping from the interior or insulations provided by a deep atmosphere, but a warm surface would not automatically mean an ocean below. A thick hydrogen atmosphere could hold heat without requiring a large water layer. A young planet might still be cooling from formation. A massive object could have a complex atmosphere and no solid surface at all. The measured glow would need to be interpreted alongside mass, age, atmospheric composition, and models of planetary cooling. Even a very cold exterior would not rule out liquid water. The ocean described through this journey survives because temperature changes with depth. Surface measurements would reveal the upper boundary, not the conditions beneath miles of ice. To probe deeper, astronomers would search for indirect signs. An atmosphere, if one remained, might contain gases released by the interior. Water vapor could emerge through fractures or cryovolcanic activity, though it might freeze or condense rapidly. Carbon dioxide, methane, hydrogen, or sulfur-bearing compounds might also reach the surface from below. Detecting such gases would not prove the existence of life. Methane can be produced through geological reactions. Hydrogen may come from water interacting with rock. Carbon compounds can be delivered during formation or released by volcanism. Each gas would have several possible origins. The value would come from patterns rather than one molecule. A combination of atmospheric chemistry, internal heat, bulk density, and evidence of active resurfacing could support the case for a water-rich interior. The conclusion would remain model-dependent until a direct measurement became possible. Surface activity might leave another clue. If warm material rose through the ice, it could create regions with different temperatures. Freshly frozen deposits might reflect or emit radiation differently from older terrain. Cracks and ridges could reveal that the shell had moved. Observing such features would require resolving the planet as more than a point of light. For a rogue world passing relatively near the solar system, a future observatory might detect variations as the planet rotated. One hemisphere could emit slightly more infrared radiation than another. Repeating changes could indicate clouds, surface regions, or uneven heat escaping from below. The signal would be weak. Distance would compress an entire world into a small collection of photons. Every conclusion would depend on careful calibration and on separating the planet from background stars, dust, and detector noise. A spacecraft encounter would provide far more. A probe could measure the planet's mass through its gravitational pull. It could map the surface temperature, search for an atmosphere, and examine the composition of frozen deposits. Radar or other sounding techniques might investigate the thickness and structure of the ice, though the useful depth would depend on the ice's chemistry, temperature, impurities, and internal layering. Magnetic measurements could also matter. A salty ocean moving beneath ice can respond to changing magnetic fields. This method has helped scientists investigate possible oceans inside moons of the outer solar system. A rogue planet would not sit inside a giant planet's rotating magnetic environment, so the same technique might not apply in the same way. If the rogue possessed its own magnetic field, or if a retained moon created a useful interaction, some electromagnetic clues might still be possible. Seismic measurements would offer another path. On Earth, waves from earthquakes reveal the boundaries between crust, mantle, outer core, and inner core. A lander on a rogue planet could listen for impacts, ice fractures, tidal stress, or internal geological activity. Waves crossing the planet would change speed and direction as they moved through solid and liquid layers. A network of instruments would be better than one. Several stations could locate events and build a three-dimensional picture of the interior. Heat flow probes could measure how much energy rose through the surface. Chemical analysis could identify the frozen remains of an atmosphere. and material brought upward from deeper regions. Yet, reaching such a world would be a project on a scale beyond any planetary mission attempted so far. The nearest rogue planet may be several light years away, or one could pass much closer without being detected until it had already crossed part of the sky. Unlike planets orbiting known stars, rogue worlds do not wait at a predictable destination. Their positions and velocities must be discovered before a mission can be designed. A spacecraft traveling at the speeds of present interplanetary probes would require thousands of years to cross even a fraction of a light year. Faster concepts have been proposed for small probes, including sails accelerated by powerful beams. Such designs are usually discussed for nearby star systems where the destination is bright, stable, and known in advance. A cold, wandering planet would be a more difficult target. It would need to be found early, tracked accurately, and approached by a probe able to navigate toward an object with almost no visible light. The first close study may therefore come from a fortunate neighbor. If a rogue planet passed through the outer solar system, its gravity could reveal it before it came near the planet. The planet's surveys might detect its thermal emission or observe its effects on distant stars. Even then, a close passage would still occur across astronomical distances. A world moving through the far reaches beyond the known planets could remain billions of miles from Earth. There is no reason to expect such an encounter soon. The possibility is useful because it shows how proximity changes the problem. A rogue planet that is unreachable across light years could become a measurable world if its galactic path happened to bring it near the Sun. Science often advances through such changes in distance. A point of light becomes a spectrum. A spectrum becomes an atmosphere. A brief brightening becomes a mass estimate. Enough separate measurements begin to form a physical place. The ocean would remain one of the final layers. Its existence might first appear not as an image, but as the explanation that best joins several observations. The planet would have the right mass and density. Its thermal emission would indicate continuing internal heat. Surface features might suggest movement within the shell. Atmospheric gases could point toward exchange between the interior and exterior. No single clue would be decisive. Together, they could make the hidden ocean increasingly difficult to replace with another explanation. This is how many remote worlds enter human understanding. They are not opened all at once. Their properties are approached through gravity, light, chemistry, and time. Models are tested against measurements. Some possibilities weaken, others remain. A rogue ocean would demand patience because its defining feature is concealed. The ice that protects the water also prevents the water from being seen. The same insulation that may preserve a living environment makes that environment difficult to confirm. There is a balance in that arrangement. The planet survives by keeping its inner world separate from the galaxy around it. Heat escapes slowly. Radiation is blocked. The chemical conditions change at their own pace. The ocean remains stable because the outside cannot easily reach it. From Earth, that protection looks like absence. No blue surface, no bright atmosphere, no orbit around a visible star, only a dark mass moving through a field of distant light. The task of astronomy would be to read what the darkness allows. A bent ray, a trace of warmth, a changing spectrum, perhaps one day a pattern in the ice. And from those small signs, the outline of an unseen sea could gradually take shape. The deepest uncertainty surrounding a rogue planet is not whether the surface is cold. That part is simple. Without a nearby star, the upper world would lose heat until ice, frost, and frozen gases covered whatever landscape remained. The harder question begins below that surface, where pressure, chemistry, and planetary history continue, long after daylight has disappeared. A buried ocean does not require the planet to remain warm everywhere. It requires only that heat moving outward from the interior meets a shell thick enough to slow its escape. Between the cold of space and the warmth of rock, there may be a depth where water stays liquid. That depth can shift as the planet ages. The ocean may thin, its salinity may rise. Its contact with the seafloor may weaken or become concentrated into isolated regions. Yet for a long interval, the liquid layer could remain a stable part of the planet's interior. This is why the idea of a hidden ocean matters. It widens the range of places where liquid water may exist. A world does not always need to circle at the right distance from a star. It does not always need a surface washed in sunlight or an atmosphere warmed from above. In some cases, habitability may depend more on insulation and interior energy than on the brightness of the sky. That does not mean every rogue planet contains water. Some may be dry, some may be gas-rich. Some may have formed with little rock, little ice, or too little long-lived heat. Others may have lost their water before ejection. Small worlds may freeze completely. Large water-rich worlds may develop deep layers of high-pressure ice that separate liquid from the rocky interior. The category rogue planet describes an orbit, not an environment. Two planets moving alone through the Milky Way could be as different from each other as Earth is from Neptune. One might be a young glowing giant. Another might be a frozen rocky body smaller than Mars. A third could carry an atmosphere hundreds of times deeper than Earth's. The possibility of an ocean belongs only to the worlds whose size, composition, water inventory, and thermal history allow it. For now, astronomers do not know how common those worlds are. Microlensing surveys have shown that low-mass objects can travel without obvious host stars, but each event offers only a narrow view. Direct imaging has revealed young planetary mass bodies, though these tend to be much warmer and more massive than the old rocky planets imagined here. The hidden ocean remains beyond direct observation. It belongs not to a discovered population, but to a physically plausible outcome supported by what is known about ice, planetary heat, and subsurface oceans closer to home. The moons of our own system have already changed the way scientists think about water. Europa, Ganymede, Callisto, and Enceladus each show that liquid can survive far from the warmth that reaches Earth. Their energy sources are not identical to those of a rogue planet. Tidal heating plays a central role for some. Their sizes, compositions, and orbital settings are different. Still, they demonstrate the larger principle that a frozen surface does not reveal the full thermal state of a world. A rogue planet would carry that principle beyond a star's domain. Its ocean, if present, would be maintained by a balance that no observer could see from outside. Radioactive decay would continue inside the mantle. Heat left from formation would move toward the surface. Water would transport part of that energy. Ice would regulate the rate of loss. Nothing about the process would be hurried. The planet could cross thousands of astronomical units, while only a thin new layer froze onto the underside of the shell. It could pass through changing regions of the galaxy, while mantle currents completed only part of their slow circulation. A moon could move through millions of orbits, while the deep ocean changed by a small amount. The world would be in motion on every scale, yet most of that motion would be too gradual to see. This is one of the difficulties of planetary science. Human attention is drawn toward events, impacts, eruptions, launches, discoveries, sudden changes in brightness. But many planetary environments are built by processes that do not arrive as events at all. Heat leaks, ice thickens, atoms decay. Rocks alter in contact with water. Orbits shift by small amounts over long spans. A hidden ocean may owe its survival to the absence of drama. The shell remains because freezing is slow. The interior remains warm because cooling is slow. Chemical gradients remain useful because water and rock continue interacting at rates that can persist. Even the planet's journey between stars may be uneventful for most of its history. This makes the world difficult to imagine from the surface. There is no horizon lit by dawn. There may be no atmosphere left to scatter starlight. The ground could be covered by nitrogen frost, carbon dioxide ice, water ice, or a mixture shaped by the planet's earlier climate. Impact scars would accumulate. Cracks might open where the shell contracts or where heat rises from below. But the most active environment could lie far beneath all of it. There, water may circulate through darkness under pressures that would crush any ordinary vessel. Minerals may form where heated fluid meets colder ocean. Salts may collect as ice excludes them. Warm pockets may appear and disappear above changing regions of the mantle. If life exists there, it would be hidden twice. First by the ice, then by distance. No telescope now operating could identify a microbe beneath the surface of a rogue planet. Even confirming the ocean would require measurements more precise and more varied than those available today. The planet would first need to be found, then weighed, then studied for its heat, atmosphere, composition, and structure. The path from detection to understanding could take generations. That does not make the question empty. Science often begins with what known laws permit before instruments are ready to test the full idea. Models describe possible interiors. Laboratory experiments measure how ice behaves under pressure. Studies of radioactive heating estimate how long rocky worlds can remain active. Observations of icy moons show how water can persist beneath frozen shells. Each piece narrows the space of possibility. Someday, a nearby rogue planet may be identified through its motion or thermal glow. A future observatory may separate its faint light from the background and find signs of internal heat. A probe may be designed to cross the distance, though such a journey would demand technologies and patience beyond current planetary missions. Or the ocean may remain unconfirmed for a very long time. The galaxy can hold worlds that are physically real and observationally distant at the same time. Their existence does not depend on our ability to see them clearly. A rogue planet carrying a buried sea would not know that it had been categorized as isolated. It would remain part of the Milky Way, moving under the same galactic gravity as stars, clouds, and every other planet. Its rocks would contain elements forged before its birth. Its water may have arrived through collisions in a young system. Its moon, if one survived, would continue circling a sky with no sun at its center. The planet would not be outside nature. It would simply be outside a solar system. And beneath the surface, the oldest conditions of planetary life could continue without light, liquid water, chemical differences, warm rock, and time. Far below the frozen night, the last water keeps its own time.